All right.
The machine says so.
Okay, so it's my pleasure to introduce Nicolás Andruskiewicz, who will talk to us about Nichols algebras and abelian groups. This is part one of 2 talks that you'll be giving here at Northeastern. So talk number 2 will be tomorrow, 10:30, and it'll be about non-abelian groups. So.
Okay, thanks a lot. Thank you, Mile, for the invitation. So let me first give you a summary of what I want to do in this talk. A Bayes vector space is a vector space provided in the solution of the so-called Bayes equation. I will explain everything. This is just a synthesis of what I will do. To each Bayes vector space, one assigns a graded algebra with other structures, which I will try to explain later. And this graded algebra is called the Nichols algebra. There were other names in the literature, but I think Nichols algebra is better because it appeared first in the work of Warren Nichols in 1978. The Nichols algebra somehow generalizes the symmetric algebra of a vector space or of a module of a commutative ring. A module of a non-commutative ring. Nichols algebras are related to quantum groups. I hope to have time to explain why, how, are related to von Kirillov algebras, which appeared 20 years ago or 30 years ago, more or less. And our main interest is personally is for the classification of coalgebras with finite dimension or finite different period dimension. This I will not explain, these relations. And the problem is that when you are given a Bayes vector space to actually compute the Nichols algebra and to decide whether this Nichols algebra is finite dimensional or has finite GK dimension or whatever property you want, usually is very difficult. Tomorrow at the end of the talk, I will discuss some examples where we don't know nothing, we don't know what to do. Very small examples which are completely open. And in case you will ask me if you tried with GAP, yes, we tried with GAP and we could not give any answer with GAP. Okay. And along the way, I will give some other definitions of Nichols algebra, which may, I will give several definitions that may be useful too. There is, to my understanding, there is no way to attack the determination of a Nichols algebra for an arbitrary Bayes vector space. I have to assume that this Bayes vector space has some special shape. This addresses me to the point where I consider classes of Bayes vector spaces. So far, the main classes we understand are those of diagonal type, which are related to quantum groups and quantum supergroups. Those related to the compositions with blocks and points, I think I will not have time to explain this. And to rack type, this I will explain tomorrow. In this talk, talk today, I will give an overview of the main definitions and I will discuss some features of the first 2 classes and mainly of the first class, which means diagonal type. So I think on this like a machine where you have an input and an output. The input is a Bayes vector space. So the Bayes vector space is related to the quantum Young-Baxter equation, an equation that was introduced many years ago by Young and Baxter independently. And the equation is as follows: you have a vector space V, you have an linear invertible automorphism R of V tensor V, and the Young-Baxter equation is this equality: R12, R13, R23 is equal to R23, R13, R12, as an equality in V tensor 3, in GL of V tensor 3, where R12 is R tensor identity, R23 is the identity tensor R, and R13 is the same, but the one of the identity in the second place. This is called quantum because there is another equation called the classical Yang-Baxter equation, and this classical Yang-Baxter equation sometimes can be quantized and some to a solution of the quantum Yang-Baxter equation. And there is also a parameter-dependent quantum Yang-Baxter equation, which I did not talk about in this. So the Braid equation is similar to the quantum Yang-Baxter equation. So you have a vector space and you have a invertible linear transformation of V tensor V. We say that C satisfies the Braid equation if C tensor the identity, identity tensor C, C tensor the identity equals the same in a different order. Identity tensor C, C tensor the identity, identity tensor C, as linear automorphisms of V tensor 3. In this case, we say that VC, so the pair VC is a braided vector space, and C will be called the braid. The standard example was something that we used many times in undergraduate course is the usual flip that sends X tensor Y to Y tensor X. This is clearly a solution of the braid equation, but even more, it's a symmetry, as I will explain in the next slide. So the relation between the braid equation and the quantum Yang-Baxter equation is given by this equality. If R is in GL V tensor V and C is a composition of tau with R, then R is a solution of the quantum Yang-Baxter equation, if and only if C is a solution of the braid equation. Now, why braided vector spaces are called like this? The braid group in N strands is given by the following presentation by generators and relations. You have N-1 generators, sigma 1, sigma N-1. And if I and J are far one from the other, then they commute. Sigma I and sigma J commute. And if they are next to the other, then one has this relation sigma I, sigma J, sigma I is equal to sigma J, sigma I, sigma J. By definition, there is a group epimorphism from Vn to the symmetric group Sn, which sends sigma I to a transposition I plus 1. Now, suppose that you have a braided vector space Vc, and then the definition of the braiding implies that the group Vn, the braid group Vn, acts on V tensor N in the following way. Given the generator sigma I, it goes to the identity C in the place I plus 1, and then the identity. And most, if not all, applications of the quantum Yang-Baxter equation arise from this representation. Tau is a solution of the braid equation, and I say that, of course, tau square is identity. In general, if one has a braided vector space such that C square is identity, this is not always the case, of course, then we say that C is a symmetry. Then the action of the braid group on Vn, on V tensor N, factorizes through the symmetric group Sn. Now let's recall what is the symmetric algebra. The input are now the symmetries. So suppose first, let me remind you very quickly, you have V and the transposition tau, which is the usual flip. You consider the tensor algebra of V. Then there is an action of the symmetric group on Tn of V, which is V tensor N, given by the formula I gave before, and this is the usual action that we know from undergraduate. So from this action, we extract the symmetrizer. It's a map Q that goes from TV to TV, from the tensor algebra to itself, which is the sum over n bigger or equal than 2 of Qn, where Qn is the sum over all elements of S in Sn acting on Pn tensor V. If the characteristic, so it's kind of integral. So if the characteristic of the field is 0, the symmetric algebra of V is the quotient of P of V by the kernel of the symmetrizer. Now, everything that I said here applies. We only need to have the representation of the symmetric group on Tn of V, so it applies for any symmetry C, so for any solution of the Braid equation such that C squared is the identity. Then one defines the symmetric algebra respect to C of V as T of V tensor the kernel of the symmetrizer, which is defined in this way. Let me quickly go through the following example of a symmetry which is not the usual transposition. Take V as C2-graded vector space, also called supervector space. We say that this in VI, where I is 0 or 1, is homogeneous of degree I. And then we define the transposition, which I denoted for the moment S tau. So S tau goes from V sense V tensor W to W tensor V, perturbed by -1 to the degree of V, degree of W. So if the usual transposition is either V or W are in V0, and if both of them are in V1, is minus the transposition. And then one extends this by linearity to all the vector space. This is a symmetry. There are two particular cases. When V is V0, then the supersymmetry is just the usual transposition, the flip. If V is all of V1, then the super transposition is minus the flip. If the characteristic of K is 0, then the supersymmetric algebra defined, as I said before in the previous slide, is the tensor product. There is an underline, which I will explain in a moment, of the symmetric algebra of V0 with the exterior algebra of V1. And this underline of the tensor product means that when you switch, you have to take into account the super trace. If the characteristic of P of the underlying field is positive, then one has to replace the symmetric algebra of V0 by the quotient by the P powers of the elements of V0. Then, if the dimension of V1 is n, I observe that this has dimension 2 to the n, and in characteristic P, it has S of V0 has dimension P to the n. This means that the symmetric algebra is not always finite dimensional, infinite dimensional. It could be many things.
So, sorry, when you say one has to replace S of V0, what do you mean that for the previous statement to hold, that's what you have to do?
Yes, so here is the symmetric algebra in the usual sense that you divide only by the quadratic elements.
Yes.
And this is in the sense that the supersymmetry. In the sense that you to have.
No, I understand, but when you say one has to do that, one has to do that in order for what? For the previous isomorphism to hold, so that SSTV is isomorphic. No, just one line up.
Yeah, this is to get is my mistake. It is to get the Nichols algebra. Right?
So one has for reasons that are not clear to us yet.
Yeah.
Okay, okay, fine.
I will come back.
Okay, yeah, that's fine.
It was my mistake. I was thinking. Okay, now I take a braided vector space, which I do not assume anymore that this is symmetry. So the only thing I assume is this equation C tensor of identity, identity tensor C, C tensor of identity equal to the same in the different order. And for that, I will define the braided vector space. I will define it in the brutal, simplest way, and then I will give two more definitions. So the key fact is that the group epimorphisms from Vn to Sn admits a theoretical so-called Matsumoto section, which goes from the symmetric group to Vn. So this is the M is defined as follows. You take an element of the symmetric group, you write it as a product of the simple transpositions, and you take the same definition above. this is not a group homomorphism because sigma square is not going to the identity. But it's a well-defined theoretical map. Then for every n, define the quantum symmetrizer by the following formula. Q to the n is the sum over S in Sn of M of S. And define Q from T of V to T of V as the sum of all the Qn's here. And define brutally the Nichols algebra of VC as the quotient of T of V by the kernel of Q. At this point, there is no reason to believe that this is an algebra, because one has to do something to understand that it's an algebra. But it is, and there's a conversion. I will not explain why this is an algebra, but let me stress the following things before going to more to a different definition. Let me set I of V is the kernel of the symmetrizer. So from now on, I will use I of V for that. This is a homogeneous subspace which starts in 2. And this is an ideal of T of V. This is equivalent to what I said before. Then the Nichols algebra turns out to be homogeneous, clearly, graded, and the homogeneous component of degree n is the quotient of Tn of V by Jn of V. So I am not saying nothing very deep. If the characteristic is 0, then the ideal I of V and C is a symmetry, then the ideal is generated by the degree 2 homogeneous component. And in this case, it can be shown that, of course, B of V is quadratic, but it can be shown that it is a Koszula. Characteristic of P is positive and C is a symmetry, then this answer to your question. You do not need to have the Nichols algebra to be quadratic, because even for this usual transposition, you have to add the fifth powers. In general, the ideal is very hard to compute. We do not know, except in some situations, which is clear, it's not known a priori whether it will be finally generated or not. And in fact, it could be not finally generated, or it could be even the zero idea.
Nicholas, can you say in characteristic P where the identity x to the P equals 0 comes from? Like you define the ideal very explicitly. Can you just say like where exactly it comes from?
Give me 5 minutes and I will tell you. When the second definition is clear.
Okay.
The dimension, so what are the problems you want to solve about this Nichols algebra? Essentially, there are 2 problems or 3. The first is more or less one is a part of the second. The first problem is when the dimension of B of V is finite. Containing this, because we are usually assuming that the dimension of V is finite. When is the dimension, the Gelfand-Kilo dimension of B of V is finite? And the third definition, the third problem is when you know that this is finite or this is finite, give an efficient set of generators of the ideal J of V and a suitable basis of B of V. At this moment, this problem is only, the solution of this problem is known only for Nichols, for B of diagonal type, which I will explain later in the definition. And these problems come from the classification of finite dimensional coalgebras or of coalgebras with finite Gelfand-Kilo. But before I will describe the Nichols algebra in a different way. First of all, let me remind you that Drinfeld introduced a method to construct systematically braided vector spaces. He did that introducing for any Hopf algebra H, let's say H finite dimensional to avoid technicalities. He defined a new Hopf algebra D of H, which is called the Drinfeld double of H. And any Drinfeld double of H comes naturally with the braiding, so that it becomes a braided vector space. And any braided vector space will arise in this way by the Faddeev-Reshetikhin-Tartaglian construction, provided that this is rigid. I do not want to explain what is rigid. It's a condition that is needed and was explained by these two persons. This is Faddeev-Reshetikhin-Tartaglian constructed by algebra. And to have a Hopf algebra, you need an antipode, and to have an antipode, you need rigidity. And this equivalent. Okay. Now, I did not give the specific definition of D of H because I only need to consider the representations of D of H, and this is better explained through the notion of Dieter-Drinfeld module. So, given a Hopf algebra H, a Dieter-Drinfeld module consists of a vector space with two structures. One is an H module, so it takes into account the algebra structure of H, and the other is an H comodule, which takes into account the coalgebra structure of H. And I will use this notation as in Sweetlegs. Delta of V is V minus 1 tensor V0. This means that this part is in H and this part is in V. Then delta of HV, these two structures should be related by one relation, and the relation is the following: delta of H acting on V, so the multiplication and the co-multiplication should obey this formula. This is a braided tensor category, meaning that you have for every V and W a map from V tensor W to W tensor V, given by this formula, and I will show you later what happens if H is a group algebra. And since this is a braided tensor category, in particular, any V, which is a Dieter-Drinfeld module, is a braided vector space by this formula. The category, as I say, the category of Dieter-Drinfeld modules is equivalent to the category of representations of the double as braided tensor category. Now, let me give quickly a couple of examples of Dieter-Drinfeld modules, which explain why we are looking at the classes I will look later. First of all, if gamma is a group, I take the category of Dieter-Drinfeld modules of a group algebra K gamma, and an object in this category is a gamma graded vector space, so V has a decomposition direct sum over G in gamma of V, and V is a gamma module, as usual, and the compatibility says that the action of G on the elements homogeneous of degree H gives the elements homogeneous of degree GH G minus 1. So this relation formula boils down in this case to this equality. And then any such Dieter-Drinfeld module over K gamma becomes a braided vector space by the formula C of V tensor W equal to G acting on W tensor V, whenever V is homogeneous of degree J. In the case that gamma is abelian, then GH G minus 1 will be equal to J, and then a braided Dieter-Drinfeld module over an abelian group is just a gamma graded gamma module. So the grading is of gamma module. For instance, if you have an abelian group and assume that as and you have a V which is Dieter-Drinfeld module, and you assume that this as a gamma module is semi-simple, which is always the case when the characteristic is 0 and gamma is finite, Then in this case, there exists a basis of V and the family of elements in gamma and the family of characters, multiplicative characters of gamma, such that the action is given by the characters and the coaction is given by the elements of the V. And in this case, the braiding is given by C of xi tensor xj, so this is the basis that realizes the action and the coaction, as I said. This is given by qij xj tensor xi. And if qi where qij is this evaluation of the character kj on the element gi. Braided vector spaces like this, I will be called of diagonal type. Conversely, any braided vector space of diagonal type can be realized over as a Lietuvos unified module over k gamma for many gammas, or for many suitable abelian groups gamma. Now, if you have a braided tensor category, there is a notion of Kopf algebra in the tensor category, because the braiding allows you to say what it means that delta is multiplicative. Then, for instance, the tensor algebra T of V is a Kopf algebra in this braided tensor category. And I remind you, T of V has many different Kopf algebra structure. There is a usual Kopf algebra structure with a one co-multiplication, but the co-multiplication I am referring to here is not the same one because we're using the braiding to switch. Okay, the Nichols algebra, D of V, which I define it as using the quantum symmetrizer some slides ago, can be shown that it is the unique isomorphism graded Kopf algebra V with the following properties. First property, it is connected, meaning that I forgot a zero here, meaning that V0 is K. It depends on V in the sense that V1 is isomorphic to V as a Lietuvos module. Now, there are the two fundamental conditions. One is with respect to the algebra structure, and the other is with respect to the coalgebra structure. With respect to the algebra structure, we say that B is generated in degree 1. So B1 generates B as an algebra. In particular, B should be isomorphic to T of V divided by some ideal, and this ideal will be homogeneous and will start in degree 2. The coalgebra requirement says that B1 is the primitive, is equals the space of primitive elements of B. And this is why we need to cut the P powers in characteristic P. Because if you have an element B, you say B to the P, delta of B to the P is B to the P tensor 1 plus 1 tensor B to the P by the binomial formula, which in characteristic 0, this PI coefficients will vanish. And therefore, BP2 should be 0 in the Nichols algebra. And this answers your question.
Sorry, should be 0 again, because otherwise you get too many primitive elements. Is that?
The idea of the Nichols algebra is that you have T of V divided by some idea.
Yeah.
But in the quotient, in this quotient, you should not have a primitives except in degree 1. So what in a few words, what you do is you take T of V. You take all primitives you can find, you divide by them. But then there will be other primitives. You divide by them. Then there will be more, and you go on until at some point you will have no primitives except in degree 1.
Well, can I ask one more question about the previous slides? So you mentioned that all braided vector spaces come from representations of drift-off double under some rigidity condition.
Yeah.
But if you have a finite-dimensional fuzzy triangular Kopf algebra, then a module of this form will be also braided. How
Yeah.
come that comes from a double?
Because a quasi-triangular Kopf algebra
Mhm.
is a quotient of the double.
Ah, so it's a representation that filters through the to the
Yes.
closest triangle. Okay. Mhm.
And
Yeah.
in Cadet Refutique Kantajan is dual to that.
Mhm.
What they do is they realize a braided vector space as a co-module or a co-quasi-triangular Hopf-algebra.
Mhm.
Then using the double or some trick,
Mhm.
you see that this is. So any representation of the quasi-triangular Hopf-algebra is a representation of the double, and similarly for the.
Understand. Mhm.
Sorry, I have a question. So.
Yeah.
So the first definition used only a braided vector space,
Yes,
but the second definition requires a choice, requires the presence of this Hopf-algebra H.
yes.
Is this one like more restrictive than the other one, or are they?
So the main philosophy behind that is the following. You want to know Nichols algebra for, say, inter-green modules over finite abelian groups for any finite abelian group. Say you want to know that. But what we understood is that we do not need to do it for all groups, because you are doing it several times, you are doing the same job. So in the first step, one works with braided vector spaces, and then we go to the groups when we know already the situation. But I will try to clarify this answer in the next slide, where I give the third definition. Suppose that you have a Jeta-Green module over H, and suppose and consider the class Gothic J of all J's which are graded of ideas and Jeta-Green modules of T of B. Then the generating ideal of the Nichols algebra J of B is an element of J which is maximal with respect to this inclusion. Okay. This is the definition I gave in the previous slide, turning around in terms of ideas. Now, a thing that I did not wrote here, but I could have, is the following. If instead of Gothic G, I define Gothic G prime as the family of all J's which are graded Hopf ideas, but they do not care about Jeta-Green modules, then the result will be the same. So the Nichols algebra will be defined, the Nichols algebra defined for a braided vector space and for a Jeta-Green module, give the same. You can say it commutes with forgetful functions. Okay, some other. This is the third definition. There are more definitions. One is one can define the radical of a one define a suitable homogeneous bilinear form of T of B, and take J of B as the radical of this form. This is the way how Lustig look at this. If you go to the definition of quantum group in Lustig's book, he uses a bilinear form and the radical. And this is again an Nichols algebra. This is how it is related to Lustig's work. There is also a way to work with suitable skew derivations. There are skew derivations on T of B, and to know whether or not an element belongs to this ideal, one decides this with the skew derivation. This is useful in practice. As I will explain later, in practice, you do not use the quantum symmetrizer. Okay. Another remark, which I do not want to enter into much detail, but it will be useful, is that given a Hopf algebra in this category, then there is a new Hopf algebra. So H is a Hopf algebra, R is a Hopf algebra in the category of Jeta-Green modules. Then R smash H is a new Hopf algebra, which is has a vector space, is R tensor H, and has some semi-direct or smash product and smash coproduct, and this is called the bosonization of R by E. Okay, so far for the general picture. Now I would like to explain how to compute the Nichols algebra in practice. There are several methods. The first method is by brute force. But by brute force, I mean the following. Suppose you have a braided vector space V, and I want to compute this Nichols algebra. So I need to find this ideal J of V. For this, I try to find as many homogeneous relations as possible by examination or lifting up or whatever means. And then I look at the algebra generated by V with these relations that I found by some method. If these relations are suitable enough, then this B will be a graded Hopf algebra. Try to describe and try to compute this algebra and try to check that all primitive elements are in B, saying that there are not any more primitives in B except those from B. This is tricky because the quadratic relations are easy to compute using the quantum symmetrizer because it's a kernel of the identity class C. But if you go to cubic relations, you have this. And of course, you know what happens for Gn, so it's very difficult to compute the relations of degree n, even for small n. I will give an example, assuming that the characteristic is 0, which I will assume from now on. So I look at the braided vector space of diagonal type. I repeat the definition I did before. I have a matrix Q, which entries are non-zero scalars, and VC is the braided vector space which has a basis xi, and the braiding in respect written in this basis is C of xi tensor xj is qij xj tensor xi for any aij in the index set of V. And for this braided vector space, I define xij as xi xj minus qij xj xi. And this is usually called the braided adjoint of xi and xj. And this is for A different from j. Then it can be shown these elements are homogeneous of degree 2. So the only way that they will belong to the ideal defining the Nichols algebra is that they are primitives, because they could not be primitives over primitives by homogeneity. So xij belongs to the ideal if and only if xij is primitive, and you do a very simple computation, and this is equivalent to say that qij qji is equal to 1. So whenever qij qji is equal to 1, we have already one relation for each pair ij. And now assume that qii is the order of ni, eventually infinite, but eventually 1. If ni is at least 2 and finite, then the power xi to the ni belongs to the primitive subspace of primitive elements of P of V. And again, this is shown using the binomial formula, but now the quantum binomial formula, because there will be Q's appearing in your picture. Now, there is a fact which is the following. Suppose that qij qji is 1 for all I different from j. Then take the ideal generated by all the xij's which belong to this j of v, because when I print it here, and add also the powers xi to ni will be homogeneous to degree ni, and such that this ni is finite and at least 2. Then the ideal generated by all these guys turns out to be j of v. How do you prove that? You write the PBW basis very easily, and then you check by hand that there are no primitive elements. So this is encouraging, but it gives you a false impression. No? In this case, everything is easy. You can do it by hand. In general, it's much more complicated.
So these are generalizations of pivot algebras when they go plus to the -1.
exterior algebras.
Exterior, yeah, sorry. Exterior
Yes.
algebras. Yeah,
Yes.
exterior, sorry, exterior algebras, and all plus or minus. Exterior.
Yeah,
Mhm.
this is, if all the q's are -1, you are in the symmetry case, and this is what it will be quadratic. Of course, let me again, this is not quadratic in general, no? And as soon as ni is not 2, bigger than 2, it's not quadratic.
But the condition qij, qji equal 1, that's exactly the symmetric case. That's another way to say that you're in the symmetric case. No?
No, except you will be in symmetric case only if the qi's will be 1 or -1.
Ah, okay.
Because C of xi tensor xi is not,
Yeah.
you need a mass plus or -1. So it is close to symmetric,
Okay.
but it's not symmetric. Okay. Now, second method is reduction to quantum groups. I take A, I go a bit quickly here because you all know this. I take a symmetrizable generalized Cartan matrix A, and I take a diagonal matrix D such that, sorry, here is DA. DA is symmetric. I changed the notation, I forgot to erase C. I take the associated Kac-Moody algebra, so related to a symmetrizable GCM. And I take Q, a scalar which is not 1. V is k to the theta, where theta is the size of the matrix. And I define C in GLV tensor 2 as follows. C of EA tensor EJ is EJ tensor EA perturbed by Q to the power DI AIJ. If Q is 1, I could define this, but this will give you the usual transposition. There's no interest in that. Then the theorem, which is a collection of theorems by a lot of people, by Lustig, Rosso, and maybe some, I think Schauenburg also obtained the version of the following theorem. And it has two parts. I am putting together the people that contributed to one or the other. For instance, the Concini-Cazzi processi, we use it for the second part. Heckenberger realized the second part without any restrictions on the order, because usually one says Q should be of odd order and relatively prime to 3 if you have a copy of G2, but all this is not necessary, as shown by Heckenberger. So, what does the theorem say? If Q is not a root of unity, then the Nichols algebra associated to V with this braiding is the positive part of the enveloping algebra, quantized enveloping algebra UQ of V. This is the first part of the theorem. The second part is that in that case, the ideal AJ of V is generated by the quantum set relation. And the Gelfand-Killock dimension of the Nichols algebra will be finite if and only if your initial pure algebra G will be finite. Finite and I simply the algebra. It is the first part. The second part is when Q is a root of unity of order at least 2. And in this case, V of V, at least when this can be defined, is Q plus of G. This is a positive part of the small quantum group. And the ideal is generated by, again, by the quantum set relations, but one has to have the powers of the root vector, except for small n, which is for n equal to 2, for instance, you can do that, but the relations are more complicated. Let me tell you very briefly what is the complication. The complication is the quantum set relation have support 2, so are relations in 2 letters, I and J. But if you go to n equal to 2, there will be relations with support of 3 letters, I plus 1, I plus 2. So, and this comes from the fact that the orders of the powers of the root vectors have a very small order. This makes this phenomenon clear. Again, the dimension of B of B is finite if and only A is of finite type. Now, how we use this information on the previous slide, this can be used as follows. Again, I consider a graded vector space of diagonal type, we had before, given by a basis xi and a matrix Q. C of xi tensor xi is Qij xi tensor xi. A remark is that this formula always satisfies the Braid equation, essentially because the underlying field is commutative. Now, there is the following definition, which is technical but very useful. We say that two matrices Q and Q prime are twist equivalent if for I different from J, Qij, Qji equals Qij prime, Qji prime. And this is so out of the diagonal, the symmetrization is the same, and in the diagonal, the entries are the same. And it's a lemma which says that if Q and Q prime are twist equivalent, the Nichols algebra B of V CQ with the braid defined by Q, and B of V prime CQ prime with the braid defined by matrix Q prime, they are not isomorphic as algebras or as coalgebras, but they have the same Hilbert series. So the dimensions of the homogeneous components are the same. And in particular, if one is finite dimensional, the other two. I take profit to introduce now the linking diagram of a matrix Q. The linking diagram of matrix Q is graph, decorated graph, where over I you put Qii, over J you put Qjj, and between I and J you put Qij tilde if this is different from 1. If Qij tilde is 1, which means that Qij Qji is 1, then I don't put any edge.
Is there a stronger statement behind the lemma that one algebra is a co-cycle twist from the other, and therefore this finite Hilbert series?
Yes.
Okay.
This is how it's proved. Okay. But I do not want to explain what this. Then we arrive to the following definition. Q is of Cartan type if there exists a generalized Cartan matrix A as above, such that Qij tilde is Qii to the power Aij. And with Snyder, at the beginning of our study over this, we prove if V of CQ is of Cartan type and all Qi's are roots of unity and the order of Qii is relatively prime to 210, then the dimension of B of V is finite if and only if R is of finite type. This is by the previous lemma, and the ideal A of B in this case is generated again by the quantum set relations in the proper way and the powers of the root vectors. Okay, so method 1 was brute force. Method 2, I don't know how much time do I have.
Say like 15 minutes, maybe.
15
Yeah.
minutes.
Uh,
15.
mhm.
The method 1 was brute force. Method 2 was reduction to quantum groups. Method 3 is inspired in the method 2, but this is independent. It's called the Weil group. So this method was introduced by Heckenberger 15 years ago or more. And I will try to explain the main points of this method. The first part, so again, I have a braided vector space of diagonal type with respect to matrix Q. And the first is to introduce, I would like to explain how to attach to the Nichols algebra a subset of Z to the theta, which I will call the roots of B of V. This is not difficult. It depends on the following facts. First of all, one can define a grading over the group Z to the theta of the Nichols algebra, just by saying that the degree of the elements of the basis form the canonical basis of Z to the theta. This is the first fact. The second is that this is a theorem by Harchenko. It's a consequence of the theorem by Harchenko. The theorem is much more general. B of B has a PVW basis, meaning that there is a set S inside B of B, which is totally ordered. The elements of S are called the PVW generators. And there is a function from this set S to N union or infinity. And this function is called the height. And then you form all the monomials, all the ordered monomials, S1 to the A1, S2 to the A2, until ST to the AT, where S1 is bigger than S2, bigger than ST. This is a convention. You can use the other convention, but doesn't matter. And the exponent AI should be between 0 and the height of the root SI. This is why so it's like a PVW basis of the universal enveloping algebra, but you have a function that says where you will have to truncate the.
Do you really want to exclude 0 or you allow it for the EI? The inequality EI is strictly bigger than 0.
You have to exclude it to have a basis. To have. You do not want to count the same monomial two times. Now, according to Harchenko, the set S can be chosen as formed by ZT to the theta homogeneous elements. And the last fact I need is the following. I know that the elements of S are homogeneous with respect to the Z theta gradient. So I say that the degrees of the elements of S, which is a family because it can be repeated, there will be the same the same element will be the degree of two different monomials. This family I will call the family of positive roots of the Nichols algebra BQ. And if I add the additive inverses, I will have delta Q, which is the family of roots of the algebra B of B. And there is a lemma which says that this does not depend on the basis on the set S of PVW generators. If you have another set, you will have the same roots, positive roots, of course, the same. Yeah. Now there is a following definition, which is very useful. This is due to Flickenberger. A matrix Q or the Veil vector space VCQ or the Nichols algebra associated to VCQ is arithmetic if the positive roots or equivalently all the roots form a finite set. It follows at once that the dimension of the Nichols algebra B of BQ is finite if and only if Q is arithmetic and the height takes only finite value. And we conjectured few years ago with Antion and Flickenberger that the Gelfand of dimension will be finite if and only if Q is arithmetic. And this implication is clear because you will have a PVW basis and then the associated, you take the associated graded ring with respect to some suitable filtration, and it will give you a finite quantum polynomial ring. But the other implication is probably true, and there is some work in progress by Angion and Garcia Iglesias towards establishing this. So I think that this is true, and I think that they proved it already, but the paper is not yet ready. Okay, now comes the difficult part. Given a matrix Q, I will consider, and given a pair of indices I and J, I will consider the family Cij, Gothic Cij, and the integers such that this is zero. So this is the Q number n plus 1 in the root Qii, and this is 1 minus Qii to the n, Qij, Qji. This expression appeared, to my knowledge, at least in the paper by Nichols. If all this set could be empty in principle, but if the Gelfand-Kirchhoff dimension is finite, then Rosso proved that all these sets for all A different from J are all non-empty, and this is written in in short, it's saying that Q is admissible. So Q is admissible says that each of these sets where there is some n, the set of all n such that this equality holds, admissible means that allCij's are non-empty. The second definition of Heckenberger, part of the definition of Heckenberger, says the following. Suppose that Q is admissible. Then set Ciiq equal to 2. AndCijq, you look at the minimal natural number or 0 inside this set and put a minus for I different from J. Then this is a generalized Cartan matrix. It is easy to see, and it's not difficult to see that if Q is of Cartan type, as I explained before, then the matrix CQ, which appeared here, coincides with the same A that defined the notion of Cartan type. Now, suppose that, again, I am still supposing that Q is admissible, and I consider the matrix CQ, which I explained in the previous slide, allows me to define reflections SIQ, where by definition SIQ of alpha j is alpha j minus Aijk of alpha I. When Q is of Greenfeld-Jimbo type, as I explained at the beginning, these reflections will generate the Weil group of the W of the corresponding the algebra, and by results of Lustig, they will lead to an action of the Bray group corresponding to W on the quantum group UP of G. In general, for admissible matrices Q, this is not true. But there is a weaker version, which I will try to explain in the last minutes. I still have 5 minutes, I think. First of all, think of Q as a bilinear form like this, or bicharacter if you prefer, and define a new matrix, rho I of Q. So rho I of Q is as follows. You take the element alpha j of the basis, you apply the reflection SIQ in the previous slide, you take the alpha k element of the basis, you apply the reflection SIQ, which I defined in the previous slide, and you evaluate on this the bilinear form Q. This is by definition, this is for every j and every k, so this is why you get a matrix rho I Q of jk. This Weber matrix in principle will be different from Q. It will be equal to Q when it is of Cartan type, but otherwise no. For simplicity, instead of V of VCQ, I will denote VQ. And I will realize V in the grading in the accelerated Greenfeld module over the group algebra of E to the theta, the coaction is given by the degree which I explained before, and the action is the only one that you can imagine. And then I will call UQ the Drinfeld double of this bosonization. So BQ is a Nichols algebra. I realize it here. I can make the bosonization. I get an honest Hopf algebra, normal, and I take the Drinfeld double. This is not finite dimensional, so I have to be careful of what I mean with Drinfeld double, but doesn't matter, it can be done. And the main theorem is a theorem by Heckenberger that says that the reflection SI of Q, which in Cartan case extended to an action of the value group of the Bray group on the quantum group, now gives you an isomorphism of algebras from UQ to U rho I of Q. So instead of going from UQ to itself, it goes from UQ to another UQ prime. UQ prime is rho U I of Q. You are changing the matrix, but you still have isomorphism. Again, this is an algebra map. It does not need to be. Even in the Lustig's case, it's not a Hopf algebra map. In the Lustig case, you need to take into account the quasi-triangular structure. I don't want to enter into this. But here again, it's not a Hopf algebra map. One has to take into account some quasi-triangular map. Now, assume that the Gelfand-Kirchhoff dimension is finite. Then the rho I of Q is again admissible, because if Q is admissible, if this again, if the Gelfand-Kirchhoff dimension of BQ is finite, then the Gelfand-Kirchhoff dimension of the bosonization is finite, and then the Gelfand-Kirchhoff dimension of the double is finite, and vice versa. If the Gelfand-Kirchhoff dimension of the double is finite, the Gelfand-Kirchhoff dimension of the Nichols algebra will be finite because it's an algebra. And since I have an isomorphism of algebras, we see that one has a finite Gelfand-Kirchhoff dimension if and only if the other has. And the same for dimension. So in any case, we know that the new matrix rho I of Q is again admissible. And we can prove that Cij of Q is related to Cij of rho I of Q for all Lij. So the rows are the same, but not the columns. Well, this is the quality of what I want to say. Now, enters an important character into the picture is the set XQ. You start with a matrix Q, and you apply rho I 1, rho I 2, as many times as you want, and the set of all these matrices, rho I 1 of Q, rho I 2 of Q, until rho I k of Q for any K or for any family, this set is called XQ. So XQ is a set of matrices. Rho I squared is the identity, and given any P in XQ, the Gelfand-Kirchhoff dimension of BP will be finite. Then by definition, not the set of roots, but the root system of BQ is the collection of all sets of roots delta P for any P in this set. So you have it set XQ, over each point of XQ, you have a different Nichols algebra and a different sets of roots, and you relate one with the other with the sum composition of the rho I's. Therefore, it is natural to say that the reflection SIP satisfies SIP of delta P is delta rho I of P. And I look at the groupoid generated over this set XQ by all the reflections SIP. And this is a groupoid of this groupoid. And this phi groupoid acts on the root system. So we can think of the root system as a bundle of sets over this set X cubed. So the main theorem by Heckenberger is as follows. Given a matrix Q, the dimension of V is finite if and only if the phi groupoid is finite, which means that the set XQ will be finite and the root systems will be finite in any fiber of the bundle. And if and only if Q belongs to a list. And with the help of Hiroyuki Yamane, and Hyun and myself try to understand the classification of Heckenberger, and we found that there are 4 classes. Cartan type, which I already explained, super type, this corresponds to super quantum groups. And the fact is that the Val groupoid, one can define Val groupoids for Lie superalgebra. And the Val groupoid of a Lie superalgebra contragradient, blah, 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 is isomorphic to the Val groupoid of the corresponding matrix here. This is why the name super comes. But then we realize there are other interesting examples in positive characteristic. There are some Lie superalgebras which are also contractile type, and these also have a Val groupoid, and we find out that these Val groupoids can be realized in the list of Heckenberger. So this is the next class. And finally, there are 11 which we do not know where they come from. Maybe we will find us a moment. And this is the main result about this. There's a second main result by Ivan and Hyono, who proved that for those elements in the list, he could give the defining relation explicitly, which is important for many situations. And I think I will stop now. I owe you the 4th member.
Any questions?
Yeah, I was curious. So you mentioned there was this other way of getting Nichols algebras by starting with a bilinear form and killing this radical. Can you see the bilinear form from this other? See if you start with the urgent fed control. Anyway, yeah. Can you reconstruct the bilinear form from any of these other methods?
Essentially, what you do is you have T of V, you have a T of V dual, so to speak. And you have a bilinear form between V and V dual, the usual duality, and you extend it to a duality between T of V, tensor T of V dual, in such a way that this is a Hopf algebra bilinear form. So it transforms the multiplication on the cone multiplication and vice versa. I am not entering into details. Maybe what I say is not completely right. I have to put an op somewhere, but the idea is that. So you have a bilinear formula T of V T of V dual that sends multiplication is transposed to the co-multiplication and vice versa. And the radical of this bilinear form is the ideal J of V. Now, in the case of Lustig, V and V dual are isomorphic as graded vector spaces because the matrix is symmetric. Therefore, it's a bilinear form on T of V only. And if you look at the book, he defines F prime, which is the tensor algebra, and then he takes F prime divided by some bilinear form. This is the algebra F used.
So,
But in practice, the bilinear form boils down to the derivations. The derivations are the evaluations of the canonical basis with the other guy. So more or less. So we seldom use it in any computation, the bilinear form. We use the derivation.
I guess you're hinting at, so these generalized symmetric algebras, you can always like generalize like a differential operators, it's like, or like a
Yes.
Val algebra, there's always a quantum Val.
In some sense,
Okay.
exactly, you think P of B is symmetric algebra,
Yeah.
P of B dual are the differential operators
Uh,
on this symmetric algebra. More or less it goes in that.
Okay.
Completely true. Please.
So if I started with like a simple finite dimensional Lie algebra and considered the quantum group associated to it. Any module quantum group has some R matrix that comes with it. I guess I'm wondering, what is the Nichols algebra where you take V to be like a module or a quantum group and then the gradient is given just by,
Yeah,
is it known? Like,
in some cases it's not, not in all cases. Yeah. It's it appeared several times in the literature, this question, and for G equal to SL2, you may give the answer.
but not for like general, not for like SLN.
For some weights, you can give the answer. And so for some other weights, the answer will be infinite dimension. Because what you do is you have the linking diagram and you extend it by a point. And depending on how do you extend it, it will give you something that you know or something which is has infinite greater dimension. But this is what I remember in the moment.
Okay. Yeah, thank you.
So heuristic spray group actions work on the level of symmetrizable Kac-Moody algebras. This stuff of Heckenberger actually generalizes just the finite dimensional heuristic, or it also generalizes the Kac-Moody heuristic? Or Heckenberger assumes some sort of finite root system to build a group for.
No, it does not assume. I have to think. But in principle, I think he only assumes that the groupoid is admissible.
Okay. So he doesn't assume this finite root system.
What he assumes in his main results is that it assumes that it is admissible for any. So you have Q, it is admissible, which means you have all the row i's. But then you have to assume that for all the row i's, it is also admissible, which in principle is not clear. If you assume that the Gelfand-Killough dimension is finite, this is why I expose it in this way, then automatically it is admissible by Rosso, and then you do not need to care about that. But in principle, you need that every time you move, the new matrix is admissible, means that you can go in all directions, and then all the matrices you get are also admissible, you also can get, and so on.
In particular, symmetrizable Kac-Moody would be an example because
Probably,
you
yes.
keep getting the same matrix all
Yes.
the time. So this issue about checking something recursively
Yes.
doesn't.
But in that case, you get the great action of Lustig.
I was just wondering philosophically whether this actually generalizes the Kac-Moody, and it does.
I think so,
Okay.
but better to check.
And can you say with a few words this last method that we didn't have time
There's
to-
only one more slide.
Okay, so this work was done by Schneider and me, and then by Heckenberger and Hiono 10 years ago, or more, 12 years ago, more or less. And we started to study a new problem. The next problem, the next natural problem, is to try to classify finite Gelfand-Killough dimension. For finite Gelfand-Killough dimension, the braided vector space V will not be semi-simple anymore, because the group zeta is not semi-simple. You have finite dimensional representations of zeta which are not semi-simple, of course. So this fits into this project. And the first way is to look at so-called blocks. The blocks correspond to the decomposable Dieter different modules over an abelian group. And it turns out that C of xi tensor if j is epsilon xi tensor xa if j is equal to 1, and if j is bigger than 1, is given by this formula, epsilon of j plus xa plus 1 tensor xi. So these are what we call blocks. So I get the different modules which are homogeneous, only one element G, and the action is given by a Jordan block. And we prove that the Gelfand-Killick dimension of a block is finite if and only if the size of the block, which is the dimension here, L, is 2, and epsilon is plus or minus 1. And this implication that in this case the Gelfand-Killick dimension is finite is by brute force. I will show you in the next slide why. And this implication is using filtered braided vector space. And since you allowed me to say this, the examples are the following. So epsilon L, when epsilon L is 1, 2, is the Jordan plane, which is a quadratic algebra, which is a kind of non-standard deformation of the quantum of the usual plane. And when epsilon is minus 1, what you get is an algebra which has one quadratic relation and one cubic relation. And we call this the super Jordan plane. Here x12 is the this expression. And there are no more slides.
Any last questions? All right. Thank Nicholas again.